Special relativity is based on two basic premises. Firstly, the premise after which it's named, which is the principle of relativity. So this states that speed, direction, and position, both in space and in time, are relative. So what that means is that if you want to measure your speed, if you want to measure your position, or if you want to measure your direction, you have to have something that you refer to as a reference point. So, for example, if you want to measure your position, there's nothing in your immediate surroundings that will tell you what position you're in. There's no experiment that you can perform that will tell you that. You just have to see where you are relative to other things for which you assume you know their position. And the second premise is that the speed of light is the same for all observers. So in the first part of this video, I will explain why it is that you should believe these two things. I'm going to attempt to do it without referring to any experiments that cannot be performed with the naked eye. So I will not refer to any experiment that uses specialized equipment. All that you have to do is either to look at the world as it is around you, or maybe look into the sky, see how things look. The most complicated knowledge that I'll be using, I think, is to do with facts about space, such as the fact that the Earth orbits the Sun, planets and stars rotate, and things like that. So in order to address the first part of this, the principle of relativity, let's start with the principle of relativity in terms of position. So we want to answer the question, where am I? Well, the answer to that question at the moment is that I'm in Cambridge. Okay, so this is a map of Cambridge. This shows you where I am. I'm not going to tell you exactly where I am in Cambridge, but I could do if I was prepared to give out that information on the internet. So we asked, where is Cambridge? Well, we can show a map of England, and Cambridge is just about here, and that tells us where Cambridge is. Okay, but where is England? Well, it's on the Earth, and we can point an arrow to show where precisely on the Earth Cambridge is. It's here. So when we answer the question, where am I in Cambridge, we can actually give coordinates as well that specify the exact position on the Earth. So that's 52.21 degrees north and 0.12 degrees east. That's not my exact location, by the way. That's just a point that's in Cambridge, relatively close to where I am now. Okay, but we know that the Earth rotates. Okay, so on that basis, we could say, well, my position on the Earth, Cambridge itself, is going to move, right? It rotates around the Earth's axis of rotation. And not only that, but the Earth also orbits around the Sun. So the position where Cambridge is today is not going to be the same as where it is tomorrow. It will be in a very different place, just because of the Earth moving around the Sun, and it won't even be the same in 5 minutes. It will have moved slightly around the Earth's axis of rotation. So that is why position is relative, because if we want to describe exactly where something is, we have to measure relative to the Earth, or choose some other reference point, such as the Sun. We can't just say exactly where something is, or at least there's no way to do that that seems easy. So now we move on to the related topic of direction. So which direction is the arrow pointing? Well, I think most people watching would immediately think it's pointing right. But the only reason you think that is because you're looking at it from this direction. If you were looking at it from this direction, then you would think it was pointing left. Right? So I think it's fairly well known that left and right are relative. All you have to do in order to change which direction is left and which direction is right. It's just to turn around. That's pretty easy, and it leads to a great deal of confusion in everyday life. And so this is something where it's pretty obvious that it is relative. But okay, what about this arrow? Well, I mean, surely there can't be any ambiguity here. I mean, this is just up. And yeah, I mean, if you're facing one way, if you're facing the other way, it's just up. Maybe if you're standing on your head, it won't be up, but you can tell if you're standing on your head, right? But we have to remember, as some people will be surprised to hear, the Earth is not flat, and so yes, up can be any of these directions, right? It depends where you are on the Earth. Up in the UK and up in Australia are two very different directions. And even directions such as north, south, east, and west suffer from the same problem. They don't point in the same direction everywhere on Earth. Now, there is a direction which everybody on the Earth can agree on, because the Earth has an axis of rotation, so everybody can agree on the direction that's parallel to that. If you're in the northern hemisphere, that will be north and up in some combinations. So if you're at 52 degrees north, like I am, then it will be 52. It will be to the north and 52 degrees above horizontal. If you're on the equator, it will be flat, and if you're in the southern hemisphere, it will be north and down. But even this is relative, because if the Earth moved, the actual direction of the axis of rotation in practice does not change very much. But it can happen, for example, if another planet collided with the Earth, then that will cause the axis of rotation to change. And you're still measuring relative to the Earth, because you're assuming that the direction that's parallel to the Earth's axis of rotation is going to stay the same, and you're measuring relative to that. So I think that explains why direction also is relative. And now, also in relativity, we assume that time is relative. So if we want to answer the question of what time is it, people had various ways of doing this throughout history, but nowadays you can look on the internet and you can see that it is 12:22 and 2 seconds in universal coordinated time on Tuesday, the 14th of June, 2022 AD. And this isn't actually the time now. This was the time when I made the PowerPoint, but you can look on the internet and find out what the time is now. This is very likely to be your local time plus or minus an integer number of hours. So specifically here we're told that the UK is 1 hour ahead of universal coordinated time during the summer months, including June. So at this time in the UK we would commonly say 20 past 1 in the afternoon. And so yes, 12:22 and 2 seconds universal coordinated time on Tuesday the 14th of June 2022 CE, which up until a certain point in history was always called AD and still tends to be by Christians, but other people prefer to use a less religious term for it, because AD stands for Anno Domini, which is Latin for the year of our Lord. Anyway, okay, so what are the reference points for time? So within a specific day, 12 o'clock UTC, Universal Coordinated Time, is the mean solar noon above the Greenwich Observatory in London. So solar noon means at the time at which the sun is as high in the sky as it will get across the course of a day. And we say the mean because throughout a year it can vary the exact time at which the sun is at the highest points in the sky. So the length between consecutive solar noons will not be exactly one day, but we say we say the mean if we average out across all days of the year, like the average time of solar noon will be 12 o'clock UTC. And then in terms of a year, the 21st of June at 12 o'clock UTC is the mean summer solstice in the Northern Hemisphere. So again, the summer solstice does not always occur exactly on the same day, but if we take an average across all years, then it should be 12 o'clock midday on the 21st of June. And then for the calendar, the base year is the year of the birth of Jesus. There are some disclaimers here that these are not actually technically correct. They're supposed to be roughly correct, but if you want to be pedantic, you can read this slide. It will tell you what the actual basis of our system of time is. But there is a caveat as well on this, that, well, cosmology now tells us that the universe began with the Big Bang. So shouldn't that be an objective basis for the start of time that everybody can agree on? So like the actual time will now be 13.7 billion years after the Big Bang or whatever. And it is theoretically possible that the laws of physics could change over time. So for example, there's speculation that the speed of light could have increased or decreased since the Big Bang, but on the scale of time that we can ordinarily measure, there doesn't seem to be much of an objective change between different times. And so for the purposes of relativity, we assume that time has to be relative as well. And then, perhaps most importantly, speed is relative. So the question is, how fast are you going? Well, let's imagine that you're in one of these cars in this picture, which is admittedly quite blurred. So this is taken on the M25, which is the ring road of London, and the speed limit on this road is 70 miles per hour. So let's assume you're going 70 miles an hour. So 70 miles per hour is approximately equal to 31 meters per second. So we can say our speed then is about 31 meters per second. Well, that's all very well until we remember this. The Earth is rotating, and at the latitude of the M25, you're completing a circle all the way around the North Pole every day. And so the Earth's rotation speed at this latitude is about 290 meters per second. So this means that our speed will actually not be 31 meters per second or 290 meters per second. Like, the actual speed you're going along the road is almost irrelevant. But also, the Earth is orbiting around the Sun, and it's going all the way around the Sun, all the way around the Earth's orbit of the Sun in a year. And so the average orbit speed is actually much bigger. Again, it's 29,800 meters per second. And so this means that actually even the Earth's rotation speed is going to be negligible when calculating your total speed. And it gets even worse because the Sun is rotating around the supermassive black hole at the centre of the galaxy, orbiting it, I should say. And the galaxy, the Milky Way, is moving towards Andromeda. And that's going at an enormous speed as well. So we would have to take into account we would have to take into account all of these things. You can't feel this. I mean, nobody would actually say you're going at all those thousands or millions of meters per second just because you're going at that speed relative to something like the Andromeda galaxy. And so in the same way that we assign reference points for direction and position, we also assign a reference frame for velocities. We take something that we assume isn't moving, and that could be the Earth, even though it definitely is moving around its axis and around the Sun, and then we assume that the velocity of that thing is 0, and then calculate everything else relative to that. And that sort of raises the question, we've said all these things are relative, is there anything that is not relative? Well, the answer is yes, and an example of this is acceleration. Acceleration is the rate of change of velocity, and this is actually absolute. So one example of acceleration is rotation. So the number of times that you're rotating within a given period of time. So the number of rotations per second or rotations per minute is something that is absolute. And we have a demonstration here about how this can affect the laws of physics. So you'll see this apple juice being put into the bag, and the rotating. We see the rotation here. And we see that the bag is being pulled up. So, like from my point of view, there appeared to be this force, which we call centrifugal force, pulling up the bag. And then within this second example, from the point of view of the apple juice, there must be some force counteracting gravity because the apple juice did not fall out of the bag. And so this apparent centrifugal force must have been present for the apple juice in this second time as well. But centrifugal force is an example of something that exists only in a rotating frame. So if you're not rotating, then you won't experience any centrifugal force. But if you are rotating, then you will. And so that's why rotation is something that's absolute and not just measured relative to something that we assume isn't rotating. And so, yeah, we have, coming back to these two premises of relativity, we can tick off this first one. We've explained why we should believe this first principle of relativity. And then the second principle, which seems probably more counterintuitive than the first, is that the speed of light is the same for all observers. So all observers will measure the same speed of light regardless of how fast they're going. This is surprising because you would normally expect, for example, if you're going in a car on the motorway, then the cars on the other side of the road look as if they will be going, say, 140 miles per hour if the cars were going at 70 miles per hour. And so you should expect something similar with light, but this turns out not to work. And the reason why is as follows. So the speed of light. So there was a debate in the ancient Greek times. Some people believed that the speed of light was infinite. So examples of these people were Aristotle on the left and Heron of Alexandria on the right believed that the speed of light was infinite, whereas other people such as Empedocles believed that the speed of light was very fast but finite. And it may not seem obvious which of these things is true, but modern information theory can give us a hint about whether the speed of light is going to be finite or infinite. So in this setup here, we have two computers, so computer A and computer B. Both of them control a light bulb. So both of the computers will have instructions about whether the bulb should be on or off, depending on the environment that they see. So both of the computers will have a sensor telling them whether the other computer's bulb is on or off. So the instructions for bulb for A are if bulb B is off, then turn on bulb A. If bulb B is on, then turn off bulb A. So A always wants the two bulbs to be the opposite of each other, whereas what B wants is for them to be the same. So if bulb A is off, then turn off bulb B, and if bulb A is on, then turn on bulb B. And if we assume that the speed of light is infinite, then both of these computers will be able to get information instantly about the state of the other computer and bulb. And so this would allow for information to flow from one place to the other instantly. And so there would be no way of determining what the actual outcome is going to be, like which computer is going to win. it will be impossible to determine because we're assuming that both of them are able to react instantly to the other one. And this would be a contradiction. Like what would happen in reality, of course, is that both of the bulbs would sort of flicker on and off depending on how quickly the computers were able to control them. But there has to be some limit to this. There has to be some amount of time for which bulb A is on before bulb B turns off and bulb A notices. And I may have got that the wrong way around. Before it has to be corrected to something different, effectively. So this means that the flow of information can only take place at a finite speed, which would suggest that the speed of light is not infinite. So, okay, if we're assuming that the speed of light is not infinite, then another question comes up, which is, does light always travel at the same speed? Like, is it possible for some light to travel at one speed and other light to travel at a different speed? And the answer to this question is yes. So it has been determined that light can go at different speeds when traveling through a medium. This is probably breaking my promise at the beginning of the video slightly because this is something that you need equipment to measure, but we're just saying that it could be possible. We don't have to prove it actually is possible for these purposes. And that would make sense because if it's traveling through a medium, then it makes sense to measure its speed relative to that medium. So that explains why things might be different there. However, what about when light is traveling through a vacuum? So in that case, there's no medium that it's traveling through, and so there doesn't seem to be any frame of reference for velocity that's different to any other. And so we have a thought experiment that can tell us things about this. Let's imagine that there was a star, and some of the light emitted from the star is slow and some of it is fast. So in this experiment, we see that the slow light from when the star was further left was observed by this person at the same time as the faster light from when the star was further right. And so this observer should see light from the star coming from two different points in the sky. But when we look up into the sky and observe the stars, what we see is this. Each star we observe as a tiny point of light. We don't see something like this, where light from when a star is in one position and at another position are seen at the same time. Now, pictures like this can be taken through using a long exposure camera, and so this really shows the effects of the rotation of the Earth, that the stars appear to rotate throughout the sky. But we don't see this at any given time, and so that would suggest that all of the light from a single star is going at the same speed. Although there is a note that because light can go at different speeds through any given medium, this can actually be observed because the last part of the journey of the light is going through the Earth's atmosphere, and so this leads to the effect that's commonly called twinkling, which is where the light from a star becomes brighter and dimmer, depending on the effects from the interference from the Earth's atmosphere. And so this would suggest that the speed of light in a vacuum is indeed constant. However, if the speed of light has different values for different observers going at constant speeds, then we actually can find an absolute way to measure speed. This will contradict our previous statement that speed is relative. So, for example, if we have two observers, one observes the speed of light to be x and the other observes the speed of light to be y, then we could measure their speeds relative to the light. So the first observer we could say is traveling at the speed minus x, and the other is traveling at a speed of minus y. I'm not sure if you can see that or not, but relative to the light, the second observer is traveling at a speed of minus y. And so this would contradict our assumption that there is no absolute velocity, because light would be something objective that everybody can agree on to measure speed relative to, and that doesn't appear to be the case. It doesn't appear that there is any absolute velocity. or absolute speed, I should say. This contradicts our statement that there is no absolute speed. And so the conclusion that we draw from this is that the speed of light is actually a constant of the universe. It's not something that depends on any individual's perspective. It's something that is a constant. And so this means that our second assumption is satisfied as well. We also have this other assumption because there are a couple of other assumptions that relativity uses, but ones that are not stated so clearly perhaps. Another assumption is the principle of inertia, which is that a particle that is not subject to any external force will move at a constant velocity. And this is true at least from the point of view of an observer who is themselves going at constant velocity. And we have a demonstration of this effect here. Effectively, when I let go of the water bottle, it does not just fall onto the floor. It carries on moving at the same velocity that it was. And there is actually an external force in this case, but that just means that it will go along a parabola rather than a straight line, and with this small period of time, it will be close to a straight line. Okay, so now we get on to the more mathematical aspect of this video. So the next section may be a bit confusing to people who don't have as advanced a knowledge of mathematics. Because these are the sort of conclusions that we can draw from the assumptions of relativity. So the first thing is called a Lorentz transformation. So the question is, if I have a way to measure space, so I have a coordinate system for space, so I have coordinates in space and in time, and then some other observer is also measuring space and time with their own coordinates. What will their coordinates look like compared to mine? So if we consider two observers, S and S prime, moving at a constant velocity, if one observer sees another particle, so a particle that is neither S nor S prime, moving at a constant velocity, then the other one will agree that it's moving at constant velocity. So the reason for this is if the particle is subject to no external force, both observers will agree on that, and so therefore they will both agree that the particle is moving at constant velocity. So let's say at a certain point in space and time, observer S describes the coordinates as x and t. So x is the space coordinate and t is the time coordinate. And observer S prime describes the coordinates as x prime, t prime. We're also assuming that space only has one dimension, just to simplify things a little bit, but you can pretty easily extend it to the three-dimensional space that we live in as well. And so the transformation xt going to x prime t prime therefore takes straight lines to straight lines. So if one observer sees something as a straight line, that will mean that the ratio of space to time is constant, which means that the particle's going at a constant velocity. And so the other observer will agree it's going at a constant velocity, and therefore will agree that it's also a straight line. But in mathematics, we have a word for a type of transformation of space that takes straight lines to straight lines, and it's called a linear transformation. And a property that linear transformations are known to have is that you can express x prime and t prime as degree 1 polynomials in x and t. So effectively, some multiple of x plus some multiple of t will be x prime, and then some other multiple of x plus some other multiple of t will be t prime. And this is true for some constants a1, a2, a3, and a4. I say constants, but they do depend on the relative velocity between s and s prime. And so suppose that the velocity of s prime with respect to s is v. So from the point of view of s, observer s prime is going at a velocity of v. And so then what observer S says is the line x equals vt. Observer S prime will say x prime equals 0. The reason for this is that if observer S prime is going at a velocity of v, then x equals vt will just be the equation of motion of S prime. So since x prime is the distance between observer S prime and the particle, then that will just be 0. So we get our equation for A1 and A2. We have A1v plus A2 equals 0. And therefore, we can substitute this in and say that x prime is equal to gamma times x minus vt. So we're going to rename A1 to gamma for these purposes, because this will actually be a useful constant to use later on. Again, it does depend on v, so not strictly a constant, but a useful number. Since there is no absolute direction and gamma is a scalar, gamma cannot depend on the direction of v. So what this means basically is that gamma doesn't have a direction, it's just a number, whereas v is a velocity, so a velocity is a speed and a direction. But gamma doesn't have any direction. And so if we change the direction of v, then gamma won't change at all, because its absolute value is all that there is about it. It doesn't have a direction. So if we change the direction of the velocity, we can't change the direction of gamma. And so specifically, if we change the direction of the velocity to be the same velocity in the opposite direction, so if we change the velocity v to minus v, then gamma will be the same. And so gamma of v is equal to gamma of minus v. And so from the perspective of S prime, we can do something similar, because the observer S is moving with a velocity of minus v from S prime's point of view. We can use the same argument as we used before to get x is equal to gamma times x prime plus vt prime. So before we had x prime is equal to gamma times x minus vt, and this is kind of a similar thing. And so we have these two equations: x prime is equal to gamma times x minus vt, and x is equal to gamma times x prime plus vt prime. And so we have this equation, and we can substitute in x is equal to ct, with c being the speed of light. So because both observers measure the same value of the speed of light, we have x prime equals ct prime, because that would be the measured velocity of a particle going at the speed of light according to the observer S prime. And we know that has to be the same. So we get that ct prime is equal to gamma times c minus vt, and that ct is equal to gamma times c plus v times t. I think this should be t prime. Yeah, that would make sense. And so this means that if we multiply these two equations together, we get that ct prime is equal to gamma squared c squared minus v squared t prime. So that's from multiplying this and this together. We get c squared minus v squared t prime. So we can rearrange that to say gamma squared equals 1 over 1 minus v squared over c squared. So that's our value for gamma squared. And then if we assume that gamma is positive, then that means gamma is the square root of 1 over 1 minus v squared over c squared. And gamma being negative also satisfies the equations, but what it equates to effectively is one observer going back in time, which we're assuming is not really something that's possible as far as we know. Okay, so then we substitute in x prime equals gamma times x minus vt into x equals gamma times x prime plus vt prime, and we get this equation here, and we can rearrange that equation to get t prime equals gamma times t minus v over c squared x. And so this is effectively how we're going to work out an expression for t prime. We've already done an expression for x prime. And so that means that given x and t and the velocity v, of s prime relative to s. We have found the values of x prime and t prime. And x prime t prime is equal to gamma times x minus vt and then t minus v over c squared x. So this is the equation for how one observer will measure coordinates in space-time, given how another observer does. And so then we can go through some consequences of this. Simultaneity is when two events happen at the same time. So in Newtonian physics, it's assumed that simultaneity is just something that's objective, like either one thing happens before another or they both happen at the same time. It doesn't depend on perspective. However, in relativity, this works a little differently. You can think of a thought experiment. Let's say that somebody is in a room, there's a light bulb at the center of the room, and they see light emitted from the bulb, and it will reach the two ends of the room at the same time from that person's point of view. However, if we consider another observer who is moving relative to the room, then from their point of view, as you can see, the light hits the left-hand side wall before the right wall, if the room is moving to the right. And this is what we would expect, because in our expression for t prime, how the other observer measures time, you can have different values of t, but the same value of t prime from this equation. So this makes sense given the equations as well. And so what this means is that some observers will see one thing as happening first, some of the observers will see both happening at the same time, and it could even be that some observers see one happening first and other observers see the other happening first. So the question really that's raised is, where does this leave the idea of cause and effect? If different observers can decide different things about which event happens first, then surely this goes contrary to our intuitions that cause always follows effect. Well, fortunately, this is not an issue. In relativity, two events, so an event in space-time is a particular point in space and time. So if we consider two events, then they can either have space-like separation or time-like separation. So if they have space-like separation, then what this means is that it's impossible to be at both of the events, even if you were trying to go between them at the speed of light. So here in our animation here, we see that the speed of light was too slow to get to event B before it happened. So this is called space-like separation. Then we have time-like separation, which is where you can get between the two events going slower than the speed of light, so say in a rocket, and the light is shown for comparison. The light is going faster than the light. If it had gone a less direct route, could have got between the two events. And then you can also have null separation, which is where you can get between the two events going at the speed of light, but no slower. And so the reason why this solves our problem is because if two events have space-like separation, then they cannot affect each other. And if two events have space-like separation, then different observers will disagree about which of the events happens first. But if they have time-like separation or null separation, then everybody will agree about which of the events happens first. And so another consequence is called relativistic time dilation. So the question is, if a clock is moving close to the speed of light, how does it affect the duration of the ticks according to a stationary observer? So if we say a clock ticks every second, according to somebody who's next to the clock, then how will a stationary observer perceive this? So for an observer moving with the same velocity as the clock, there is a tick at every point where x prime and p prime is equal to 0 and n, where n is an integer number of seconds. So using our equation from before, we find that from the viewpoint of the observer who is at rest, gamma times x minus vt and t minus v over c squared x is equal to 0 and n. And so we can do some substitution from this equation, because x equals vt, since gamma times x minus vt equals 0. And so we get the substitution that gamma times 1 minus v squared over c squared times t is equal to n. but that actually simplifies to t equals gamma n, because 1 minus v squared over c squared is actually equal to 1 over gamma squared. So t equals gamma n. So from the point of view of the other observer, ticks only happen every gamma seconds rather than every 1 second. Gamma is always greater than 1. The reason for that is that we have gamma equals 1 over square root of 1 minus v squared over c squared. Since this thing is always going to be less than 1 and we're dividing by it, then we will always end up with something that is greater than 1. So this leads us to an idea in relativity which is called the twin paradox. So the idea is we have two twins, Alice and Bob, and Alice and Bob were born at the same time on the same planet, as most twins are, and Alice likes to go off on adventures going at high speed, and Bob stays on his home planet. And so one day Alice decides to take a long trip going at a velocity that's very close to the speed of light, and she takes a clock with her. So one tick of the clock will be perceived as 1 second by Alice, but by Bob it will be perceived as gamma seconds, assuming that the difference in velocity is v. And because gamma is always greater than 1, this means that the ticks will take a longer amount of time for Bob. And so this means that Bob will actually experience more time than Alice does. And so when Alice eventually comes home again, Bob could be an old man, whereas Alice may only have aged a few years, depending on how big gamma is and a few other factors, but this is at least possible. And so the question is then, well, if velocity is relative, then why is it Bob who is old rather than Alice? Couldn't we make the same argument that, well, from Alice's point of view, Bob was the one who was moving at a very high speed in the other direction, and so it should be Bob who is younger. Well, this can actually be resolved, because if Alice is going at a high velocity and then returns to her home planet, then at some point she must have accelerated. So remember, acceleration is a change in velocity, so either a change in speed or a change in direction. And so because Alice has accelerated at some point, then the laws of physics will be different for Alice at that time. And so we can't apply the same logic to her frame of reference, because her frame of reference, it's not moving at a constant velocity, it's accelerating. So that brings us towards the end of the topics that are covered in this video. There are a few things that we haven't covered. For example, how mass is affected by relativity is a big topic. There are also geometrical interpretations of relativity. So some of the things I imagine are probably still seeming quite counterintuitive, and there are geometrical interpretations that makes things make a bit more sense. Also general relativity, which considers how gravity works and how this is actually affected by space-time that we've been talking about itself. And then also I thought I'd mention quantum mechanics as an example of a theory in physics that shows that actually the principles of relativity, the assumptions that we've been making, are actually wrong. In this case, probably implicit assumptions that we've been making are wrong at the small scale. And so the predictions of relativity don't actually, they're not perfect. They don't always work at small levels. Okay, and that brings us to the end. Thanks for watching.